Okay, so yesterday we covered the topic of the turning effect of forces. Sobia, you were there. Any questions?
Yeah, I would like you to just explain this part one more time.
The whole topic?
No, this page.
This page. Okay. So, right now, what the principle of moments or right, what the principle of moments or the law of moments talks about is when a body is balanced or in equilibrium, the sum of the clockwise and the anti-clockwise moments should be equal, right? And therefore there is no resultant moment. Now, the two things I pointed out is that the sum of the clockwise moments and the sum of the anti-clockwise moments, that means that you can have more than one moment that is acting clockwise and more than one moment that is acting anti-clockwise, like I tried to illustrate over here, right? And about any point, that means that there could be more than one point of pivot, right? Or more than one resting point.
Yeah.
Then the conditions for equilibrium, meaning that there's no resultant moment, right? The thing is not moving about, is that the sum of forces in one direction should equal the sum of force in the other direction. So that is basically pointing towards the sum and any point, and that the law of moment should apply. So to illustrate that, this is what we looked at. Okay, this is a plank that is resting on 2 points A and C. Right, the center of the plank is O, and right, the entire weight of the plank, 400 newtons, is acting downwards. Okay, now this is where Newton's third law is going to come into play as well for our understanding. Right, if 400 newtons is acting downwards, the weight of the plank, that means that the 2 points where the plank is resting are going to be giving an upward force, right, a push to the plank, which in total would come up to 400 newtons, right? So whatever A and whatever B the force is, right, it would equal 400 newtons. So that is an understanding we should have based on Newton's third law. Also, when we are calculating the moment of force or the turning effect of force, we can only do it considering one pivot at a time, right? So in this case, what they're doing is that they are taking C to be the pivot, right? And then they are going to calculate, oh, what's the moment of force? So one is simple to calculate. We're going to take the weight that is acting downwards and it will produce an anti-clockwise moment, and the distance is 2 meters, right? So what's the moment of force? 400 newtons times 2 meters, that's 800 newton meters. That is the moment about O. Now, because it is balanced, that means that the moment at point A would be clockwise because the force is acting upwards. We know that. Okay, so the force is acting upwards, the moment, and because it's balanced, it's in equilibrium, so the moment would be the same. So the moment of force at point A is equal and opposite, so that's 800 newton meters. What's the distance from point C, 2 and 3? That's 5 meters. We don't know how much force is being applied, right? So that is the unknown, force P. And so to calculate that, 800 divided by 5 gives us 160 newtons. This is as far as the moment of force is concerned. Okay, the turning effect of forces. So the anti-clockwise moment and the clockwise moment are equal, right? Both are 800 newton meters, and that is why this plank is in equilibrium about pivot C.
Also, why didn't we take A as the pivot?
We didn't take A as the pivot, we took C as the pivot.
Yeah, I'm asking why didn't we take A as the pivot instead?
You could do that. You want to do that?
I thought it couldn't be that way.
Oh no, it's only because we can do one at a time.
Oh, okay. We can start with pivot A or we can start with pivot C.
Yeah,
It's either one of them.
Yeah. So okay. So now we talked about Newton's third law. So the total downward force should be equal to the total upward force because it's balanced. And so we know that the weight in total is 400 newtons. We found out the upward force at point P, which is 160. Right. So that means whatever the value at Q is, Q plus P should be equal to 400 newtons. We know what P is. That's 160. We get Q. So 400 minus 160, that gives us 240. Right? For the sake of practice, it's a good thing you brought it up. We can do this around point A. So let's do the whole thing. Oops, not new page. We can do the whole thing again, right? But taking A as the pivot. So for the sake of practice, let's do moment at O. This time this will be the clockwise moment. Okay?
Yeah.
And the moment around O will be 400 times 3. So let's do that. (400 newtons times 3 meters gives you 1200 Newton meters. Okay?
Yeah.
And this is the clockwise moment. About A. Okay. Then we need C. Right? So C is 5 meters. Right? So moment about C equals to, what's the force? Q. Right? So Q into 5 equals to 1200 because it's balanced. So the anti-clockwise moment is going to be equal to the clockwise moment. So we know that the moment of force, right, at point C is going to be 1200. So what do we get for Q? Q equals to 1200 divided by, right, so this
Which
is,
will give us divided by 5.
yeah, and so what do we get?
240.
240 newtons. Isn't that exactly what we got over here?
Yeah.
Right?
Yeah.
And so yes, right, applying Newton's third law, right, since the body is in equilibrium, right, the downward force is 400 newtons, right, so the total upward force, which is P plus Q, should be 400 as well. 400 newtons equals to P plus 240. P equals to 400 minus 240, which is what we know to be 160 newtons. Did you get the exact same values?
Yeah.
Right? So the object is stable, the values, you take it from one end or the other, it's going to be the same. Right? It's just what is your point of reference, what are you taking as the pivot, and you do the calculations accordingly.
Okay.
Is it clear now?
Yeah.
Good. And it's good you brought that up, right? So this was a bit of practice as well, right? And clarification of the concept. Now, today we will start talking about center of gravity, which is pretty much just conceptual, there, right?
Yeah.
Okay, center of gravity, also sometimes called center of mass, right? It is a point in an object where all of its mass, right, is concentrated. Right, or it seems to act through that point, all the mass. Right, and because we're talking about mass, right, and gravity, so m into g equals to w, weight. right? And so by extension, the center of gravity, center of mass is also the center of its weight, right? Obviously the weight is distributed throughout the object, right? But because the mass is all through the object as well, but there is a point where it seems to concentrate, where the effect of the mass, the effect of the gravity, the effect of the weight, right, seems to act through a certain, right? So the effect is concentrated at that point. Right, now for regular objects, or regularly shaped objects to be particular, right, the center of gravity is usually the center of the object.
Does it basically attract towards the center?
Attract towards the center, what do you mean?
You said that it's a center of gravity is like where the point of an object is where the mass is, right?
The mass is throughout the whole thing. The effect of the mass is sort of it right, you can feel the effect. It's concentrated, it applies through that point. It's not that there's no mass in the rest of the body, right?
Okay.
So
Yeah.
for example, a ruler, right, a simple example is a ruler. So straight line, right, assume this is a ruler, and right, eyeballing it, the center is somewhere here. Now because this is a regular object, right, the center of the ruler is the center of gravity. What this means, right, if you try to balance the ruler at this point, right, then if you just hold it up with the tip of your index finger or any other method, you hold it up with a string or a wire, it will be balanced, right, because the center of gravity, so the mass, right, distribution throughout is acting at this point, it is even, right, and so the mass distributed on either end of the ruler is also even, it's uniform, and so it will be balanced, as opposed to, for example, right, you try to balance the ruler from one edge, right, so if you try to balance the ruler from here, right, and so this is not the center of gravity,
Yeah.
right, and so what's going to happen is, right, you try to balance it from here, but again eyeballing it about this, okay, this is the center of gravity, so the weight of the object is acting through this point.
Yeah.
You're trying to balance it from here where the arrow is, right, and so, right, the ruler will tip over, it will not hold.
Okay.
Okay,
Yeah.
because the weight of the object in this case is, right, acting from the center, and you're also holding it up from the center, you're trying to balance it, so, right, it's fine with that. But if you're trying to balance it from any other point, right, it will tip over, right, and that's only if you're holding it from one point, right. Of course, if you're holding it up from 2 points at opposite ends, then you're basically preventing it from tipping over anyway, right?
Yeah.
But that's a different scenario.
Yeah.
Okay, the human body, right, also has its center of gravity at the center of your body, right. Now the center of your body is perhaps somewhere in the abdominal region, right, And one thing that they say in the book, right, in fact I'll share the illustration with you. I don't want to go about drawing that, so let me put that up on screen. Okay, so this is the illustration they have, and they're saying your center of gravity is near the center of your body, and the vertical line from it to the floor must be within the area enclosed by your feet, or you will fall. And to test that, you stand with your foot, one of your feet, and your arm pressed against the wall, and then you raise your other leg and you will fall over to the side. Okay, now what do they mean by, right, the vertical line from it to the floor must be within the area enclosed by your feet or you will fall? What do they mean by that? Right, that is a matter of stability, which is they discuss right after this, and so for the purpose of clarity I will discuss it now. So going back to the whiteboard,
Okay.
stability. Right, so you take the center of gravity of an object. And you draw a vertical line down to its base. Right, and for that we can take a shape, right, a regular rectangle. Okay. Move, maybe. Sorry. Right, now let's take black, and so right, this is probably the center. Okay, and we draw a vertical line down to the base. And my whiteboard is stalling. Okay, now if right, if this vertical line from the center towards the base is falling within the area that is enclosed by the base of the object. Now we've taken a rectangle for ease of understanding. It could be any object. If it is falling within the area enclosed, by base, right, it will be stable, and stable means it will not topple over. Right, but if you tilt it, so we'll need another rectangle, and we're going to rotate this guy, and yeah, something like that. And if I've got this right, center over here and draw a line, and as you can see it is falling, so yeah, it is falling just outside the base. I mean, I could tilt it further. Tilt it further. Yeah, there you go. Better. And now what's happening, that the area enclosed by the base, so that's the base. This is the area enclosed by the base, and the line from the center of gravity is outside. So the center of gravity is outside the area enclosed by the base. And in this case it will topple over. It is not stable. That means that if you tilt an object to an extent that it is tilted, but it's still falling within the area of the base. Alright, so we need a third guy, slightly tilted, not as much, slightly bigger. Yeah. Alright, and center here somewhere, vertical line down. And even though it's tilting, as you can see, the vertical line from the center is still within the area enclosed by base, which means it is still stable. Right, so it will not topple over, it will go back. So this, when you tilt it this much, right, it will actually go back to standing upright. Is that clear?
Yes.
Did the illustrations help?
Yeah.
Okay. Alright. Now, how do you increase the stability of an object? Right? You want an object to be stable. How do you achieve that? Well, there are two things, right? And they detail an experiment where you're taking a can, right? You take a can and you put it on a plank, a rough plank, to avoid it slipping, and then you tilt the plank until the can topples over, right? And you note the angle, right, at which it toppled over. And then what you do, you repeat the experiment, and this time, right, you add a mass to the can.
So what's the plank?
Plank is like a piece of wood, a long piece of wood.
Okay.
Right? So you add a mass to the can and repeat, and what you will notice is that it will it will not topple over at the same angle, right? You can tilt it much further. To a greater angle. Right? Also, you repeat the experiment and you use a can with a wider base, and you will notice the same, right? You'll be able to tilt to a greater angle, right? So I mean, this is like separate. Once you repeat the experiment with the mass in it, and then you repeat the experiment with the can with a wider base with no mass in it, just the base being wider, and you'll be able to tilt it to a greater angle. And of course, if you do like, you know, wide base plus mass, so goes without saying, right? It will. So that those are the two factors actually that affect stability, right? Factors affecting stability. One, right, is increasing the area of its base. And two, lowering its center of gravity. Now, why is it saying lowering? I didn't highlight that in the experiment. What they mention is that you have a can and you're putting in a rock or something, some sort of weight, and it's going to be at the bottom of the can, right? It's not like something that's, you're not going to fill the can with water for, you know, equivalent to a kilogram, so that's like a liter of water, right? You're going to add some weight to it that's going to sit at the base, at the bottom, right? So you added a 1 kilogram weight to it, and what you've done this way, because right, the can itself is like a few grams, it's very light, but when you added that 1 kilogram to the base, right, what you did basically is you ended up lowering the center of gravity, because now we can't say, oh well, you know, the mass is actually physically concentrated at the base, but you know, the center of gravity is at the center of the can. No, now the center of gravity is somewhere over here, okay, at the center of that mass you put in, okay.
Yes, sir.
And so that is lowered, right? For the empty can, yeah, it was at the center of the can, right? So empty can, right, this was the center of gravity for the can itself. But now that you've added the mass in, you've lowered the center of gravity, and that would make it more stable. And so you notice objects that have wide bases, like table lamps, like, you know, glasses that have wide bases, especially those wine glasses, right? They have a thin stem, and even though they're like wide in their actual the glass part where you pour in the liquid, but you can see that their bases are also wide. So there's something like, again, right? So, and then they're like that, and so you've got a wide base, and most likely the base is heavier than the rest of the glass, right? So perhaps the center of gravity is also concentrated in the base. The base is heavier than the rest of the glass, and so that's what makes these. So I mean, right, you probably wouldn't have these glasses at home, right? If you want to go to a restaurant or a hotel and try it out and say, oops, it broke, but you can, right? Now,
Yeah.
obviously, if you add a liquid in here, right, so that is adding to the mass, and that will actually make it more stable. Right?
Yes.
Okay, now, right, figuring out the center of gravity for, you know, vehicles, for example, or buildings or other objects is very important to, you know, figure out how stable they're going to be. Okay, and for example, vehicles such as race cars, especially Formula 1 cars, not
Yeah.
negative, right? You can see that, okay, I'm going to be very bad at this, right? That is its fender, something, and horrible drawing, right? I'm probably sure a grade 2 student could do better. But the point is that, the car itself is very low, and so its center of gravity is very low. And the car is wide, right? So it's got a wide base. And that's why they can actually move at those high speeds and make those turns without toppling over. You cannot do that with a regular car, right? Because these guys are very stable. And so other vehicles, especially larger vehicles like trucks and buses, they are tested, and so that's given the book, right, are tested for stability. Tested for stability, right, using a tilt test. Right, so they're put on a platform and the platform is raised using a crane up to a certain angle depending on the requirement. So fire trucks may be needed to, depending on where they're being used, they may, if it's a mountainous or hilly region, right, they might move on a tilted platform or tilted road, and so they need to be stable, right? If the fire truck topples over, then that's not going to help. Similarly for a bus, right, a bus moves through various routes and it has passengers and cargos, right? So the passengers are made up using sandbags to add weight, and then it is tilted, and the book says, right, it's tilted up to through an angle of 28 degrees. So yeah, tilted. And it should not topple over up till 28 degrees tilt, right? So stability is tested that way. Next up, right, so far so good, all clear?
Yes, sir.
Okay. Next up is we're going to talk about stable, unstable, and neutral equilibrium as far as the center of gravity. All right, so we're going to talk about equilibrium, right? And we're going to talk it in context of center of gravity. Now, this topic is not part of the O Level syllabus. It is part of the IGCSE syllabus. Okay, and so they're giving you three situations. The first situation is stable equilibrium, and stable equilibrium is when an object is moved and the object attempts to go back to its original position. Okay, the example they give for that, right? In fact, let me explain this first and then I'll go to the illustration given in the book. Unstable equilibrium is when an object is moved and so it moves further. It doesn't go back, it moves further. It's unstable. And the third is neutral equilibrium. So when an object is moved, it just stays in its new position. Right? It's going to stay in its new position. It's not going to bother going back. It's not going to bother going, moving further away. It's just going to okay, fine, new position, I'm good. How does that work out? Again, as I said, I'll take you to the book for that. So let me just put that up on screen. Again, this is for the IGCSE. Oh, come on, show up. Thank you. Alright, can you see that?
Yes.
Okay. So there you go, right? So the topic of stability in the IGCSE textbook, right? It's not even highlighted yellow, so it's part of the regular syllabus, not even extended. Whereas in the O level one, it's given as going further. So, right, I mean, you can obviously try and understand it, but it's not part of your syllabus. So, alright, I've explained the concept of it, what's happening in stable equilibrium. They given the example of a ball in a dish, right? And so the point of, and because it's a ball, the turning effect of force, the moment of force is also coming into play. And what they do perhaps is not as clearly visible. If I just zoom in, perhaps you can see that the new position of the ball is given with the dotted circle. Okay. Is that clear?
Yeah.
Okay. And so they moved it up in the dish, right? This is the point of contact, and so this is the point of moment or turning effect that the ball will face. Now, right, the center of gravity is now lying outside the point of contact, meaning its base, right? And in this case, right, its center of gravity rises. So compared to its original position, the center of gravity is now higher, right? And the ball will roll back to its original position, right? It rolls back because its weight has a moment about the point of contact, so turning effect, and it acts to reduce the displacement, so going back to its original position. That is stability. That is stable equilibrium. What's happening in unstable equilibrium? Obviously the scenario is going to be different. You're not going to have unstable equilibrium having in this scenario, right? So whether an object experiences stable equilibrium or unstable equilibrium does not only depend on its own mass or the the width of its base, but the situation itself, right? So if you've seen those people who do tricks to try to balance glasses on the tip of a straw or a fork or something, right? And
Yeah.
right, so basically that is a scenario where you are trying to pull off something with unstable equilibrium, because even though the base of the glass is wide, the surface that the glass is resting on, for example, a pencil tip, is like, I mean, it's just a tip of a pencil, and so they're trying to balance it, and so that is very unstable, right? A slight movement will cause it to topple over.
Yeah.
Right, so this is the scenario where the ball is in, and you move it, and so now the center of gravity is lower than it originally was, and so the ball will keep rolling on and fall down or whatever is going to happen next. It's a slow because basically it will move away, right? And so they explain that as, right, its center of gravity falls when it is displaced, so right, it's lower, and right, because there's a moment which increases, so right, this point there's a turning effect of the force at this point, the force of gravity, so it will cause the ball to roll, and that increases the displacement, right? And so that is unstable equilibrium. And they're also mentioning the ruler balance, right? So if you're not holding it from the center, you're holding it from the side, it will topple over, same thing. And finally, neutral equilibrium, right? So this is a state, it's on a flat surface, right? You move it to a new position, it's not doing anything, because the center of gravity is still at the same height it originally was, and it's acting vertically down, it's acting through the point of contact, so it's right at the base, which means technically it's stable, but in this case, because it's a circular object, it will not move further away, it will not try to go back, it will just rest at its new position.
Okay.
Right, that is right, neutral equilibrium. Now since we're here, right, a little, I would call it a side topic that they've given, and this, right, this balance in tricks and toys, I'm just going to show it over here in the text, and this is given for both the IGCSE and the O level. Okay, so you can see it's there and it's part of your syllabus. Right, so they're giving you ideas of making balancing toys, right? And the whole concept is, in each case, the center of gravity is vertically below the point of support of and the equilibrium is stable. So whatever the point of support is, right, the weight, in this case the can or the bulldog clip or the iron nut, is below the point of support. Okay, so that's one thing. And then they talk about a self-righting toy, right? So we all played with those. They're fun, they're interesting. Especially one that really intrigued me when I was younger is the bird that balances on the tip of its beak. Have you guys ever played with that?
No.
Okay. Have you ever played with any of these balancing toys?
I remember vividly.
Okay. Right, so a self-righting toy. So you tilt this guy all the way down, right? It will still bounce back up. And the reason for that is that it's a heavy base, so right, a lot of mass concentrated in its base. Right, the weight acts to the center of gravity. It has a low center of gravity, right, and it has a moment. So it's curved, right? So that's turning effect, and it is a moment about a certain point. And so it has a low center of gravity. We tilt it, right, it will move to the opposite direction just like the ball, right, and it will restore its upright position. So nothing complicated going on there, and that is the end of this chapter. Now, as far as the balancing toys are concerned, right, I had a video pulled up, right? So before we go into momentum, I think I can introduce the topic. But again, before we go into that, right, and if I can just do that over here as well. Okay, good. Alright, so entire explanation of doing this. Now here's a particular trick. I hope it loads.
ClickUp is the AI.
Yeah, no.
Okay. So you want to take your fork and use your spoon to do this. We're going to pry the two prongs and the middle of the forks up a little bit, because what we want to do is wedge our spoon in the center, just like so. Kind of push it in as much as you can, because you want them to stick together just like this, okay? Once you do that, stick your matchstick into the middle prongs of the fork, just like this. Take your matchstick and place it on your glass. You need to find a good position to balance it. I need to go a little bit forward. Perfect. And this is how you balance a fork and a spoon on a glass with a single matchstick. This is the magic of irregularly shaped objects when it comes to center of mass. Sometimes the center of mass, the average position of all the mass in the object, is outside of the object. That would be where we would put our balancing point. But if we didn't have our matchstick, we wouldn't be able to do this. So our matchstick allows us to reach that balancing point, to reach that center of mass, allowing us to balance our fork spoon system on our glass. Now here's something really fun you can do. Take a lighter and light your matchstick. Parents and adults, because we're using fire, you want to exercise caution here. You should be the one to do this. What do you think will happen? When I light my matchstick on fire, what will happen to our fork and spoon? Make your guesses. Woo! It stays right in place. And watch, I can just knock off the end, just like that. Because our balancing point wasn't towards the center of the glass, our balancing point was right on the edge of the glass. So all we need is a single touch point from the match to the glass to balance our spoon and fork. And that is how you balance a fork and a spoon on the edge of a glass with a matchstick. If you're having a hard time getting this to work, just play with different forks and spoons because there's variability in the weight and how bendy those prongs are, so just try different ones until you can get it to work. Okay, let's try this again. Oh! Now watch this. How cool is that? It looks like it's like defying gravity. That's basically the nose of the bird right there. These are the wings. That's the nose of the bird. Thanks for playing with balance with me. If you like this one, be sure to check out my best-selling Stay Curious and Keep Exploring book series for...
Alright, how cool was that?
Yeah.
But I don't understand that, like, it's only touching the glass. It's like if all of the mass is pulling down on the other side.
That's the fun thing. Alright, so what's happening is, if I just go back to that tab, and rewind. Just a sec. So if I just rewind this and I can get it to that position where they're showing the matchstick.
Like that. Because our balancing point wasn't towards the center.
Alright, that's as good as a position we can get. Right? What's happening over here is, right, the mass of the fork and spoon being, right, transferred through the matchstick and are being applied downwards at that point.
Center of the...
Okay?
If it was only a match without this spoon and a fork,
It wouldn't balance. No.
yeah, even that wouldn't balance, but it can balance with even more weight.
Oh, there are like so many things that you can make with physics that actually seem to defy physics, but they're actually spot on, right? And one thing that you can do, I'm probably going to get the spelling wrong. Tensegrity. Okay, thank you, Google. Alright, now obviously I'm just mentioning this, it's not part of your syllabus at all, right?
Yeah.
And so just check this out.
Yeah, I heard about this.
Want to create an online store but not sure what to do next? With managed WooCommerce hosting from Hostinger, you can skip the complex.
What's the criteria for a tensegrity structure? Well, the first thing is it needs to have components that are in compression and components that are in tension. So these rods here are in compression, they're being compressed, they're made of aluminium, they're really good at that. And they've got these wires here that are in tension. Wires are really good in tension. The other criteria for a tensegrity structure is there needs to be at least two separate parts that are in compression that are entirely separate from each other and only joined by parts that are in tension. So here, for example, the bottom part and the top part are separate from each other. They're not touching except for these wires that are in tension. So this is an example of a tensegrity structure as well. You've got these 6 wooden rods that are in compression. They're only joined together by these elastic parts in tension, so the wooden parts aren't touching each other at all. And I'll tell you a bit more about this later on because there's some really interesting stuff about this particular structure. But first, just to go back to the table, it's really counterintuitive, isn't it? It's all being held together by wires. Like, how is that possible? And that's what I want to explain in this video. So here's the 2D version, and I built it with elastic bands instead of wires because I want you to see how they bend and stretch when you try to collapse the structure. So why is this structure stable? Well, any way that you try to collapse the structure, it turns out that at least one of the elastic bands ends up being stretched. And when you stretch an elastic band, it pulls outer cables to remain stable, but 3 points fix a plane because there is some flexibility flexibility in the wires, and it's a really strange sensation actually, because you can move it laterally like that, but it's really strong in the up and down position. It's very strange. You can even set up a bit of simple harmonic motion in the top. Isn't that cool? Actually, with this design, you can tune the stiffness of the wires. So if I let out section once in inverted commas to tilt this way, but it can't because of these cables in tension, and it's only stable for as long as you don't push it in this direction. It's not an official Lego product, but if you search for tensegrity Lego, you'll find one if you want to make one for yourself. Strictly speaking, for a structure to be classed as...
Alright, so that was just an example of how cool and mind-boggling physics can be when applied to different structures, right? So it is like with the push it will collapse, but at the same time it is strong enough to actually hold up weight, and it's just right two objects pulling on each other. That's basically what it is.
Yeah.
Okay, so coming back to the whiteboard, okay, we don't have time for momentum. What I will go into, however, is finding the center of gravity for irregularly shaped objects. Okay, it's pretty simple. It's nothing complicated about that. So, right, can you see the whiteboard?
Yes.
Okay.
No,
No?
but now I can.
And I've lost the nib of my pen. Oh, found it. Okay. So, as you mentioned, right, for regularly shaped objects, the center of gravity is usually the center of the object. Depending on where the mass is considered, it can be lower, right? But what about irregularly shaped objects? Now, this is an experiment that is given, a practical that is given in your text resources. Right, and so for example, you've got something like this. It's an irregularly shaped object. So what are you going to do? You're going to pin it up on a wall or a soft board or something, right, from one point, and let it hang loosely. Right, so assuming that I've pinned it up and it's hanging loosely, and I'm going to use what is called a plumb line. Right, so a plumb line is a weight that is attached to a string. And what that does basically, right, the string isn't very straight over here, but what it does, so if I just remove that dotted line and make a proper line out of that, and I get 90, good enough. Okay, and so because the weight is pulling down, right, the gravity is pulling down on the weight, pen, it will, right, there will be a reverse pull on the string, and that will keep the string absolutely straight. And so use a plumb line over here, right, you hang it, and then what you do is you draw a line over that, right, and so let's call this points, right, A and B, and then you take another point, for example, right, somewhere over here, and you hang it. So I'm not going to you obviously rotate it, you hang it, it's going to, right, be in a different position. You use the plumb line again, and right, you draw, for example, it's hanging this way, and you draw a line, and you can repeat this like 2-3 times, right? You can hang it from here, right, and you will see, so as many lines as you take, right, you will notice the more lines you take, they will not all be right, whatever the shape of the object is, obviously it's irregular, but what you will notice is that the more lines you take, they will all be intersecting at one point, and that point of intersection is the center of gravity for an irregular object. Clear?
Yes.
Sobia?
Yes, sir.
Ibrahim?
Yes, sir.
Any questions?
No.
No.
Okay, good. Then we'll call it a day, and right, then we'll catch up with momentum and move forward next week. Then, all right. And the meeting ended just in time. All right. Bye bye.